Hi, today I would like to talk about the electron and the hydrogen atom. One of the important things to know about the wave function of particles is that it must be the same for a given position in time, which means if it's at the same position, it must have the same value. This means that if S represents a position of a particle in a bound state around a nucleus and R is a radius from the nucleus, the wave function psi of S comma t must be equal to psi of S plus 2 pi r comma t, and that's where S is a position, R is a radius from the nucleus, and t is time. And the reason why this is true is because 2 pi r will bring you right back around to the starting point, and so these two positions are the same. And so now if we let the wave function, the psi S comma t is equal to a times e to the I over h bar p of s minus h times t, that must be equal to a times e to the I over h bar p times s plus 2 pi r minus h times t. And that's where h bar is Planck's constant, p is the magnitude of the momentum, s is the position, r is a radius from the nucleus, capital H is a Hamiltonian which acts like energy, and t is time. So now if we divide by this part, we're going to get psi of s comma t is equal to 1, which is equal to e to the I over h bar 2 pi r times p, which is equal to cosine of 2 pi r times p over h bar plus I times sine 2 pi r times p over h bar. And only time this value can be 1 is when whatever is in here must be equal to 0 or 2 pi or 4 pi or 6 pi or some integer multiple of 2 pi. So we can say now 2 pi r times p over h bar is equal to 2 pi n, where n is some integer. So now if we divide by 2 pi, we get r times p over h bar is equal to n, which implies then that p is equal to h bar times n over r. So these are the possible values for the magnitude of the momentum. However, the Heisenberg uncertainty principle means that the momentum can never be exactly 0, so n must be an integer that's greater than or equal to 1. Okay, now for this next part, we'll assume that the mass of the nucleus is infinitely greater than the mass of the electron. This will simplify things because it treats the nucleus as if it's motionless, so it won't add to the kinetic energy. We'll now look at the Schrödinger equation, which is in this case p squared over 2m times state vector plus v times state vector is equal to h times state vector. And again, this here is a state vector. P squared over 2m is the kinetic energy, v is a potential, and h is a Hamiltonian. And I'll put a caret over each of these to symbolize that these are actually operators. Now, the only time that the operator can be treated as scalars, which is what we're looking for, is when the electron is in an eigenstate, or at least a superposition of eigenstates. And in this case, solving for these scalars will give us the eigenvalues. So we're going to do that by dividing out this state vector, and we get p squared over 2m plus v is equal to h. Okay, And so now, if we substitute in h bar times n over r for p, okay, we will get h bar squared n squared over 2m r squared plus v is equal to h. Now, because the magnitude of the force in a field, okay, such as this, where the electron and the proton are in each other's electric fields, it means then that the magnitude of force in the field is minus the partial derivative of the potential energy with respect to the radius. We can find the potential energy in this case, and by finding the magnitude of the Coulomb force on the electron and then integrating over the change in radius. So basically what we're going to do, we're going to take the Coulomb force, and then we're essentially going to integrate it with respect to r, and that should give us the potential energy. Okay, so basically the Coulomb force of an electron that's attracted to a proton is minus e squared over 4 pi r squared epsilon sub 0, and that's where e is the electric charge of the electron, r is the radius, and epsilon sub 0 is essentially the electrical permittivity of the vacuum, or essentially the capacitance per given meter in the vacuum. So if we take the negative of this and integrate it with respect to dr, we will get e squared over 4 pi r squared epsilon sub 0 dr, and if we integrate that, we will get minus e squared over 4 pi r epsilon sub 0, and this is the potential energy. Okay, so now what we're going to do, we're going to put it back into the Schrodinger equation, and that will give us essentially h bar squared n squared over 2mr squared minus e squared over 4 pi r epsilon sub 0 is equal to h, which is a Hamiltonian. So now if we take the partial derivative of this with respect to dr, what we will get is minus h bar squared n squared over mr cubed plus e squared over 4 pi r squared epsilon sub 0 equals 0, because mind you, the Hamiltonian is constant because energy is conserved. Okay, so now if we solve for r, what we will get is r is equal to 4 pi h bar squared n squared epsilon sub 0 over m e squared. Okay, and this is the formula for the radius of the hydrogen atom. Now the variable n represents the energy level of the electron, so if we let n equal 1, this will give us the radius of the hydrogen atom in its ground state. This is what's called a Bohr radius. Now, if we use the correct values for the constant, then this radius turns out to be about 5.9 times 10 to the minus 11 meters. Now, if we substitute this radius, the formula for this radius here, back into the Schrodinger equation, we will get the following. We will get h bar squared n squared over 2m times m squared e to the fourth over 16 pi squared h bar to the fourth n to the fourth epsilon sub 0 squared minus e squared over 4 pi epsilon sub 0 times m times e squared over 4 pi h bar squared n squared epsilon sub 0 is equal to h. And this will simplify down to m times e to the fourth over 32 pi squared h bar squared n squared epsilon sub 0 squared minus m times e to the fourth over 16 pi squared h bar squared n squared epsilon sub 0 squared is equal to h. Now if you notice, the potential energy term here is minus 2 times the kinetic energy term. So this means then now that the total energy, okay, which is h, is equal to minus m times e to the fourth over 32 pi squared h bar squared n squared epsilon sub 0 squared. Okay, and this is essentially the energy of the hydrogen atom. So now if n is 1, okay, again that will be the ground state. So if you notice, the total energy is negative because the electron is bound or trapped by the nucleus. A zero positive number would mean that the electron is free of the nucleus. Now if we let n equals 1, as I stated before, we get the ground state energy of the electron in the hydrogen atom, which is about minus 13.6 electron volt, which means that it will take about 13.6 electron volts to ionize a hydrogen atom from its ground state. Also, the only variable left in the formula is n, which can only have integer values. This means that essentially the energy level in with the hydrogen atom in a bound state is quantized, and essentially that's why it's called quantum mechanics, because the energy can only have discrete values. Anyway, that is all I have for now. I hope you find it informative, and I'd like to thank you very much for watching.